In physics, energy is a property of objects which can be transferred to other objects or converted into different forms, but cannot be created or destroyed. The ability of a system to perform work is a common description, but it is difficult to give one single comprehensive definition of energy because of its many forms. For instance, in SI units, energy is measured in joules, and 1 joule is defined mechanically, being the energy transferred to an object by the mechanical work of moving it a distance of 1 meter against a force of 1 newton. However, there are many other definitions of energy, depending on the context, such as thermal energy, radiant energy, electromagnetic, nuclear, etc., where definitions have derived that are the most convenient. Common energy forms include the kinetic energy of a moving object, the radiant energy carried by light, the potential energy stored by an object's position in a force field, elastic energy stored by stretching solid objects, chemical energy released when a fuel burns, and the thermal energy due to an object's temperature. All of the many forms of energy are convertible to other kinds of energy, and obey the law of conservation of energy, which says that energy can be neither created nor be destroyed. However, it can change from one form to another. 4. Closed systems, with no external source or sink of energy. The first law of thermodynamics states that a system's energy is constant unless energy is transferred in or out by mechanical work or heat, and that no energy is lost in transfer. This means that it is impossible to create or destroy energy. The second law of thermodynamics states that all systems doing work always lose some energy as waste heat. This creates a limit to the amount of energy that can do work by a heating process, a limit called the available energy. Mechanical and other forms of energy can be transformed in the other direction into thermal energy without such limitations. The total energy of a system can be calculated by adding up all forms of energy in the system. Examples of energy transformation include generating electric energy from heat energy via a steam turbine, or lifting an object against gravity using electrical energy driving a crane motor. Lifting against gravity performs mechanical work on the object and stores gravitational potential energy in the object. If the object falls to the ground, gravity does mechanical work on the object, which transforms the potential energy in the gravitational field to the kinetic energy released as heat on impact with the ground. Our sun transforms nuclear potential energy to other forms of energy. Its total mass does not decrease due to that in itself, but its mass does decrease when the energy escapes out to its surroundings, largely as radiant energy. Mass and energy are closely related. According to the theory of mass-energy equivalence, any object that has mass when stationary in a frame of reference also has an equivalent amount of energy whose form is called rest energy in that frame, and any additional energy acquired by the object above that rest energy will increase an object's mass. For example, if you had a sensitive enough scale, you could measure an increase in mass after heating an object. Living organisms require available energy to stay alive, such as the energy humans get from food. Civilization gets the energy it needs from energy resources such as fossil fuels. The processes of Earth's climate and ecosystem are driven by the radiant energy Earth receives from the Sun, and the geothermal energy contained within the Earth forms. The total energy of a system can be subdivided and classified in various ways. For example, classical mechanics distinguishes between kinetic energy, which is determined by an object's movement through space, and potential energy, which is a function of the position of an object within a field. It may also be convenient to distinguish gravitational energy, thermal energy, several types of nuclear energy, electric energy, and magnetic energy, among others. Many of these classifications overlap. For instance, thermal energy usually consists partly of kinetic and partly of potential energy. Some types of energy are a varying mix of both potential and kinetic energy. An example is mechanical energy, which is the sum of kinetic and potential energy in a system. Elastic energy in materials is also dependent upon electrical potential energy, as is chemical energy, which is stored and released from a reservoir of electrical potential energy between electrons and the molecules or atomic nuclei that attract them. The list is also not necessarily complete. Whenever physical scientists discover that a certain phenomenon appears to violate the law of energy conservation, new forms are typically added that account for the discrepancy. Heat and work are special cases in that they are not properties of systems, but are instead properties of processes that transfer energy. In general, we cannot measure how much heat or work are present in an object, but rather only how much energy is transferred among objects in certain ways during the occurrence of a given process. Heat and work are measured as positive or negative depending on which side of the transfer we view them from. Potential energies are often measured as positive or negative depending on whether they are greater or less than the energy of a specified base state or configuration, such as two interacting bodies being infinitely far apart. Wave energies, kinetic energy, and rest energy are each greater than or equal to zero because they are measured in comparison to a base state of zero energy, no wave, no motion, and no inertia, respectively. The distinctions between different kinds of energy is not always clear-cut. As Richard Feynman points out, these notions of potential and kinetic energy depend on a notion of length scale. For example, one can speak of macroscopic potential and kinetic energy, which do not include thermal potential and kinetic energy. Also, what is called chemical potential energy is a macroscopic notion, and closer examination shows that it is really the sum of the potential and kinetic energy on the atomic and subatomic scale. Similar remarks apply to nuclear potential energy and most other forms of energy. This dependence on length scale is non-problematic if the various length scales are decoupled, as is often the case. But confusion can arise when different length scales are coupled. For instance, when friction converts macroscopic work into microscopic thermal energy. Some examples of different kinds of energy. History. The word energy derives from the ancient Greek nu epsilon rho gamma epsilon iota alpha energia, activity, operation, which possibly appears for the first time in the work of Aristotle in the 4th century BC. In the late 17th century, Gottfried Leibniz proposed the idea of the Latin vis viva, or living force, which defined as the product of the mass of an object and its velocity squared. He believed that total vis viva was conserved. To account for slowing due to friction, Leibniz theorized that thermal energy consisted of the random motion of the constituent parts of matter, a view shared by Isaac Newton, although it would be more than a century until this was generally accepted. The modern analog of this property, kinetic energy, differs from vis viva only by a factor of 2. In 1807, Thomas Young was possibly the first to use the term energy instead of vis viva in its modern sense. Gustav Gaspard Coriolis described kinetic energy in 1829 in its modern sense, and in 1853, William Rankine coined the term potential energy. The law of conservation of energy was also first postulated in the early 19th century, and applies to any isolated system. It was argued for some years whether heat was a physical substance, dubbed the caloric, or merely a physical quantity, such as momentum. In 1845, James Prescott Joule discovered the link between mechanical work and the generation of heat. These developments led to the theory of conservation of energy, formalized largely by William Thomson as the field of thermodynamics. Thermodynamics aided the rapid development of explanations of chemical processes by Rudolf Clausius, Josiah Willard Gibbs, and Walther Nernst. It also led to a mathematical formulation of the concept of entropy by Clausius and to the introduction of laws of radiant energy by Joseph Stefan. According to Noether's theorem, the conservation of energy is a consequence of the fact that the laws of physics do not change over time. Thus, since 1918, theorists have understood that the law of conservation of energy is the direct mathematical consequence of the translational symmetry of the quantity conjugate to energy, namely time, units of measure. In 1843, James Prescott Joule independently discovered the mechanical equivalent in a series of experiments. The most famous of them used the Joule apparatus. A descending weight, attached to a string, caused rotation of a paddle immersed in water, practically insulated from heat transfer. It showed that the gravitational potential energy lost by the weight in descending was equal to the internal energy gained by the water through friction with the paddle. In the International System of Units, the unit of energy is the joule, named after James Prescott Joule. It is a derived unit. It is equal to the energy expended in applying a force of 1 Newton through a distance of 1 meter. However, energy is also expressed in many other units not part of the SI, such as ergs, calories, British thermal units, kilowatt-hours and kilocalories, which require a conversion factor when expressed in SI units. The SI unit of energy rate is the watt, which is a joule per second. Thus, 1 joule is 1 watt-second, and 3,600 joules equal 1 watt-hour. The CGS energy unit is the erg and the imperial and US customary unit is the foot-pound. Other energy units such as the electron volt, food calorie or thermodynamic kcal, and BTU are used in specific areas of science and commerce.